So we know how to identify Bronsted-Lowry conjugate acid-base pairs, and we know that these acid-base reactions are based on proton transfer because we reviewed our Bronsted-Lowry definitions, right? But they're also in acid-base equilibrium, which is basically what this entire lecture is about. And so therefore, the net direction of a reaction can be influenced by these conjugate acid-base pairs. And the question becomes, well, how? Well, how they're going to be influenced is their relative strengths. And so where do we get our relative strengths? It is going to be something that you have to memorize when we get to like specific strong acids, strong bases, and some weak acids and bases. But when it's talking about net direction in relationship to conjugate acid-base pairs, there is a particular figure you can use to help you be able to just immediately read the figure and then figure out whether they're strong or weak based on what you had, okay? And so that's how we're going to get through for this portion. As we go along in the lecture and we learn more about specific strong acids and bases, I'll be help guiding you to tell you which ones you really want to remember, because it's going to be important to have a handful of them that you really know, that you'll mainly see as we go out throughout the semester, okay? So the net direction is going to depend again on those relative strengths of the acid and bases that we have within the acid-base equilibrium system, okay? So if we're thinking about equilibrium, we got to go back to our equilibrium constant K. So we know that K is equal to the concentration of products divided by the concentration of reactants. And so when K is greater than 1, that means that we're going to have a shift towards the right, towards the products, because we have a larger amount of products in our numerator. And if K is less than 1, then we're going to have a shift to the left towards reactants, because again, our reactants are going to be more numerous than our products, and that gives us a smaller K value. Overall, the reaction is going to favor the formation of whatever is the weaker acid and the weaker base. So our goal is to have an example to get into it. So when we have our example here, we have H2S plus NH3 is in equilibrium to form HS minus and NH4 plus. So we saw H2S already. We saw H2S Spider-Man. And we saw that H2S Spider-Man created a conjugate acid-base pair with HS minus Captain America, as we see here. And we know that we had Spider-Man as an acid, and we had, of course, Captain America as a base. But we really didn't know their strengths, right? We knew they're an acid-base pair, but we would not know their strengths. And then we had our stronger base, which can be like NH3 Iron Man, for example. And this stronger base, according to Bronsted-Lowry, is going to have a lone pair and have the ability to accept a proton. And when it accepts a proton, it's going to create a weaker acid, which is NH4 plus. And so if we have to figure out the net direction of a reaction, we have to get details about these conjugate acid-base pairs and figure out which ones are stronger or weaker. And this is not us specifically saying this is strong, this is weak. This is all relative. And so how do we understand what is something that's relative? We go by a spectrum. And so you see here on this chart, we have an arrow going up, and that's signifying acid strength as we go up the chart. And then we have an arrow going down, signifying base strength getting stronger as we go down the chart. And so we find our H2S acid, and then we also find its conjugate base, which is HS minus. Here it is here. We then find our NH3 base and our NH4 plus. Here it is here. And then we ask ourselves, which one is stronger? And why is this going to be important? Well, think about it. If NH4 plus is stronger, that means it's going to have the ability to give up its proton and produce NH3 more, right? And so again, you'll see NH3 being produced. But if H2S is the stronger acid, then H2S is going to be giving up its proton and forming HS minus. And so we'll see more of this produced. And of course, we'll see that proton and more NH4 plus being produced as well. Because again, this is all about proton transfer. Something has to be donated, something else has to be accepted, right? And so when this H plus is gone, this NH3 can then accept it and form that NH4 plus. And so we have to ask ourselves, which one is going to be able to give up the H plus first? And the one that's going to give up the H plus first is the stronger one. So based on our spectrum here, H2S is higher up. And so it's going to be stronger than NH4 plus. Therefore, it's going to give up its H plus and be used up in the reaction way before the NH4 plus does. Okay, folks? And we have to do the same thing for the bases. The bases are opposite. So we have HS minus here, and then we have NH3. As you can see, NH3 is stronger. And so NH3 is going to accept protons and produce NH4 plus more than H minus is going to accept a proton and form H2S. Okay? And so because of that, we have a stronger acid in H2S here and a stronger base in NH3. And then we have a weaker base in HS minus and a weaker acid in NH4 plus. Therefore, since we have all weaker acids and weaker bases on the right, then the entire equilibrium or the net direction of the reaction is going to be towards the right. Okay? And so, of course, we have to get more examples so that we can be able to understand this better, but we want to have more details as well. So just remember, if H plus is stronger and it's giving up that proton, right, and forming HS minus, then you have to ask yourself, which one is stronger between the bases? We know that NH3 is stronger, so instead of H minus, grabbing that proton again and forming H2S, we're more likely to have NH3 use up those protons and then form NH4 plus. And so all we're going to be doing in a couple of examples is using the relative strength or our understanding of relative strength to answer a couple of example questions. Okay, folks, let's go ahead and get into the compound. All right, we come to our first example in the Avengers compound about net direction of reactions. So let's go ahead and read it. Predict the net reaction and whether Kc is greater or less than 1 for each of the following reactions. And it says assume equal initial concentrations of all species. We're not dealing with any right tables here. We're just answering the question. So first thing you have to do is identify those conjugate acid-base pairs. And of course, look at our figure here to see which one is going to be stronger. Once you know which one is stronger, then it's going to be easier for us to be able to figure out where's the weaker acid and bases and where the stronger acid and bases and figure out where the net direction is. Once we know our net direction, then we can say, okay, if we're going towards the products, that means K has to be greater than 1 because products in the numerator is going to be higher. And if the weaker acids and bases are going to be in the reactants, then we know K is going to be less than 1 because we're going to have way more species in the reaction level. So we have to basically go ahead and identify those as well. And that's how I would approach this question. Now, in this kind of type of question, are you going to be responsible for memorizing this whole table? Absolutely not. I will be providing this for you if you have these type of questions, right? So don't worry about that. Okay, but as far as particular strong acids and strong bases, as we go along, yes, I'll be telling you about that. Okay, so let's go ahead and get into it. First things first, you want to identify what the acids are and the bases are. Here, we know acids are going to have H plus in this formula. We're still going with the Bronsted-Lowry definition. And so we know this is our acid here, and then therefore this is our base. And so we're trying to get our conjugate acid-base pairs. That means we are trying to get rid of one proton here. And if I get rid of one proton, what is left? Well, I'm going to have a hydrogen left, PO4. And then again, I have to increase my negative charge, so I'll have a 2 minus. That means my conjugate acid-base pair for this one is going to be HPO4 2 minus. So this is also a base. Next, we're going to do it the same thing for our base. We know that we have NH3 here. NH3 has lone pairs and has the ability to accept a proton here. When it accepts a proton, it's going to then form NH3 here. We're going to accept a proton. It's going to form NH4 plus. So when it does that, we form NH4 plus, which is an acid. And so we do the same thing that we did before. We take our information, our H2PO4 minus and HPO4 2 minus, and we find those on our scale here. So I'm like H2PO4 right here, and then HPO4 2 minus. So that's one of them. And then we have NH3 and NH4 plus. You know, NH4 plus and NH3. So we have both of our individual conjugate acid-base pairs. Now the question becomes, which one's weaker? Which one's stronger? Whichever one is weaker or stronger, then we know we can again get rid of them. So for our acids here, we know that H2PO4 minus is going to be stronger. So I'm going to put an S here. And the NH4 plus is weak. I'm just going to put a W. Okay. Overall, I'm just going to put an arrow to show you where the net direction is. That's how I'm kind of approaching this. Next, let's go ahead and look at our bases. So we see that NH3 is a stronger base than HPO4 2 minus. So overall, the reaction is going to shift to the right. If it's shifting to the right, that means our products are being produced more, and so our K value is greater than 1. Those are our answers. Shift to the right, and then, of course, our K value is greater than 1. Let's do it for the next one. Again, we are looking for our acids and bases, and you have to ask yourself, well, wait a minute. Both of these have H in their formulas, so how do we know which one is an acid or a base? Well, we also have to look at charge as well. With this one here, if we're looking at water, I first would kind of look for my bases. That's the first thing I would do, look for my base. And we also have our chart here as well. So you're like, okay, I can find HS minus. I see HS minus here. It's automatically going to tell me that is a weak base too. And we could go back off of just some details about conjugate acid-base pairs. You go back and think about those, that video, because you have to be able to distinguish. Again, some people go straight to this picture. Well, let's talk. We know that an acid is going to have H in its formula, right, and be able to donate a proton. That looks like that could be possible for both of these. So then you say, well, let's go what a base is. A Bronsted-Lowry base is going to have those lone pair electrons and be able to accept a proton. So we know we have lone pair electrons on our oxygen here, right? Have our lone pair electron, all right? So we have our lone pair here. Let me make sure I can actually write it, all right? And then we also have lone pairs in our sulfur here. So you're like, okay, well, that's not going to help us. So then we got to get more layers of information. We talked about conjugate acid bases, right? Acid base pairs, for example. We specifically said conjugate bases have one fewer hydrogen and it has an increase in the number of negative charge, right? So between both of these, which one has a negative charge? That's going to be our HS minus. And so I'll automatically say that is my base here. And also, don't forget H2O storm. She's infiltrate. So you definitely want to figure out what this is before you start looking at water, because it can be both. You have to make sure you have your answer. I'm going to go again off of the conjugate acid base pairs and then thinking about that base having the ability to have a fewer hydrogen and more of a negative charge. And of course, you can also look at the photo. Okay, so that's going to make water my acid. And if this is a base, it has the ability to accept a proton. The proton is going to come from water, right? And once it accepts the proton, it's then going to form the acid H2S. Same thing here. If our acid here is water, water is going to donate a proton and be left with OH minus. So we also have the base OH minus here. We're going to do the same thing and figure out, let me get a good color here, the strength of these conjugate acid base pairs. So we have H2O and we have OH minus. And then we're going to have our H1 OH minus here, boom. And then we have our HS minus and our H2S. Okay, boom. So when we're talking about stronger acids, let's go ahead and look at the strength of the acid. H2S is going to be a stronger acid. Okay, so H2O is going to be a weaker one. Next, let's look at HS minus and OH minus. OH minus is going to be a stronger base, and this is weaker. So automatically, our reaction is going to be in the direction of the reactants, or shift to the left, okay? And that means our K value is less than 1 because we have more products than reactants. And that's how we'll be able to answer this type of problem. All right, folks? So again, with this problem, you most likely will be given a chart like this. Outside of this type of question, you would have to know or be able to understand whether or not you have a strong, weak, or stronger weak acid or stronger weak base. That's what I'm thinking as well. Okay, folks? So we'll just go along as we go along. Let's get into another example before we go, because I know that we see this example here, which is more like you reading all the details. I want to get into a more molecular view too, so you can kind of have a different, or conceptualize it differently. That's what's in my head, right? So let's go ahead and do that. Okay, this says that given that HX, which is blue and green, so let's go ahead and identify that really quick. Let me get mine here. This is going to be HX here. And they said that this is stronger. So they're already telling us this is a stronger acid, okay? And it's telling us it's a stronger acid than HY. And HY is blue and orange. So here's an HY. And this is a weaker acid. Which scene, 1, 2, or 3, so they're giving us 3 scenes, best represents the final mixture after equimolar solutions of HX and Y minus are mixed. So remember, this is a question about net direction based on conjugate acid-base pairs. And instead of giving you a reaction, they're giving you molecules, and you have to use these molecules to come up with your own reaction. So that means, and they're already telling you what your reactants are. They're telling you you're going to have HX plus Y minus. And we already know this is the stronger acid, right? And this is going to be in equilibrium to form HY, okay, which we know because it's going to, this is the base, it's going to accept the proton. So we know it's going to form HY. And then we're also going to have X minus that's left over from the HX donating a proton. And so what else did they tell us in the question about HY? They said this is a weaker acid. So automatically we're seeing strong, we're seeing weak, okay? Now we really can't go back to the chart, right, and figure out what any of these species are because they're all variable. So we have to basically kind of use our advantage and our knowledge of conjugate acid-base pairs or relative strength of conjugate acid-base pairs to help us. And what we notice is a little trend, and I'll go back to that to show you. So we're back in the previous question really quickly to go back to this chart here. What we notice is a little trend as well that shows you that the stronger the acid or base, the weaker its conjugate acid or base. So even if you aren't given particular species and given variables like we saw in our molecular scene, we can still use this little trick here, this way for us to expand the information to help us be able to layer stuff. Okay, folks? So if you even see to verify, we have H2S, which is a stronger acid than H2O, for example. And the stronger the acid, the weaker the base. H2O has a stronger base, OH minus, than we have HS minus here. So again, if you keep that in mind as you're going through with more molecular scene, that'll help you be able to answer questions. So let's get back to our question. And so if I know I have a stronger acid here, that means its conjugate base is going to be weak. So I know that this is going to be weak. And if this is a weaker, right, acid, that means its conjugate base has to be strong. And so if both these sides are strong and both these sides are weak, what direction will the reaction go? The reaction is going to go to the right, towards the products. Okay, and so if it's going to the right towards the products, and I have to figure out which one of these scenes are going to represent that, then I need to find a scene that has more what? Has more of the products. So what are my products? My products are X minus and HY. And so I'm looking for more HY to be in one of these scenes. And so HY is that blue and orange, right? And so I'm looking here, I have 1, I have 2, I have 3. Here I have 1, 2, and 3. So they're in equal amounts here. That's not what we're looking for. Let's move on. I have 1, 2, 3, 4 here, and I only have 1 and 2 here. So this represents having more reactants. That's not what we're looking for. By process of elimination, you know it's going to be number 3. But let's verify. That's what you always want to do, verify. So we count this as 1, 2, and then this is 1, 2, 3, 4. This is good. We have more products, which makes sense because we have weaker acid and base in the product side. And so our reaction is going to shift to the right, and therefore our K value is going to be greater than 1 because we have more products. Therefore, only scene 3 is consistent with what they gave us in the question. So when they have a molecular scene, you first want to start labeling whatever they give you so that you can know which one is which, and then you want to set up a reaction. You need to know what the conjugate acid-base pairs are. And so once you know that you have an acid, you can basically donate a proton to figure out what its base is going to be, and that's going to be for either direction since we're in equilibrium. That's your start. Then you can go and use the chart before to figure out which is stronger or weaker, but instead of doing that, you can use that little caveat, which we know. Stronger acids and bases are going to produce weaker conjugate acids and bases. So if they give me something that's stronger, I know automatically the base I create is going to be weaker. If they give me something weak, I know that the conjugate acid or base I create is going to be stronger. So having those little details and allowing us to layer that information can give you these type of questions, which we give molecular scenes, or more straightforward questions like we saw in previous. All right, folks?